card-carrying demographer close. I'm even less close, though, to being a card-carrying climate scientist. I try to make that clear, even though every once in a while someone calls me a climate scientist. But I happen to work with some very brilliant climate scientists who were kind enough to lend me some of their slide decks. And this much I do understand, so I can at least lecture on it. So Richard Seeger is a close colleague and collaborator. We work on climate mobility work together, the NSF and DoD work. Jason Smerdon is another climate scientist. Radley Horton and I have worked a lot on urban heat related risks. And he's also a collaborator on some of my climate mobility work. And then John Mutter. But they all work at the Lamont Doherty Earth Observatory at Columbia. Or have worked there at one time. So here we have an image of the distance of the different planets from the sun. And what I think is important, here, the main message is, you might have heard the term, the Goldilocks zone. So the Earth is in this perfect distance in orbiting the sun at a perfect distance to maintain temperatures that are habitable. And habitability is a growing research topic and agenda. It started really thinking about these planets, right? Which planets might have actually supported life at some point. Some people think that Mars at one point supported life. So if you look at these three planets, basically the Earth, without any atmosphere, just based on the distance from the sun, would be average annual temperature around the freezing point. Okay, that would be its average annual temperature. Whereas the average annual temperature of Venus is around 50 degrees Celsius, so extremely hot. And for Mars, it's like -50, so extremely cold. So that's just based on our distance from the sun. But there's this thing called the atmosphere that has a number of effects. One is trapping heat, and I'll talk about that in a moment. The other is its reflection as well. So the more cloud cover, the higher reflectivity you have. And so when you add in the Earth's albedo, that is the degree of cloud cover, you find that the Earth would actually be, with all that shortwave radiation from the sun being reflected back out to space, we'd actually be down here at -18 degrees Celsius. Very cold, not very nice, right? Average annual, that's not good. So what about if you add in the greenhouse gas effect? So if you add that in, you actually get into this even better Goldilocks zone of about average annual temperatures of 15 degrees Celsius, right? So the greenhouse effect is tremendously important to our planet. And how does it work? Well, I've given away a little bit by talking about shortwave radiation coming into the planet from the sun. And it comes down. Some of it gets immediately reflected back through the atmosphere and out to space. Okay, that's from various types of cloud cover. Some of it comes down and hits the surface, right? And when it hits the surface, some of it is absorbed in the surface, and some gets also reflected back through things like ice cover, right? So high albedo surfaces are those reflective surfaces where the radiation gets reflected. But as the thermal surface and of the Earth, as the surface warms up, some of that is also lost, reflected back into the atmosphere through long wave radiation. And that long wave radiation can kind of bounce around. It goes up towards the clouds, comes back, etc. But that's what retains our thermal properties in the Earth. Without the atmosphere and without clouds, etc., we would be dead. Basically, we would not be able to survive on this planet. So that's all good, right? Greenhouse gases, are actually good thing, right? They keep us alive, but now we've got too many of them. So we'll talk a little bit more about that in a moment. This is just for those who are more scientifically inclined to think about the electromagnetic spectrum. Professor Rahman could go on a lecture about just the electromagnetic spectrum, but this is a little bit visualizing, how the shortwave radiation comes in, and then the outgoing thermal long wave radiation goes out, and then how the different gases either absorb or let that go, escape out to space. So this all goes back to work by Fourier, Tyndall. You might have heard of the Tyndall Center, and Arrhenius, who all basically started hypothesizing about the effect that the atmosphere has on the climate, and the ways in which this idea that we actually live. We call them greenhouse gases because if you've ever been in a greenhouse, right, the shortwave radiation comes in through the windows, and then you're stuck in there, and it becomes hotter and hotter as time progresses. So a lot of this science has been around for a long time, but a hypothesis is that and this was going back to their time, really. They were thinking about this already. If you start burning fossil fuels, it will increase the level of CO2 in the atmosphere, which will cause the temperature of the Earth to rise. Is CO2 in the atmosphere increasing? This is the question. I think everyone in the room knows the answer. So this guy Keeling, Charles Keeling, decided that he would create an observatory on Mauna Loa in Hawaii, and he would start measuring the levels of CO2. So we have him to thank for our understanding of the increase of CO2 in the atmosphere. So he started in the late 50s, mid-50s, and he started measuring CO2 when it was down around 316 parts per meter, parts per ppm, parts per meter? Million. Thank you. Someone correct me, please. It's a long day. So I'm just keeping you on your toes. Okay. Right. So anyway, this is what it showed in 2015. And now, so what you can see is before present was Keeling's estimates, really the rise since, 1955 roughly till 2015 or so. You see it's just like one straight up line, right? Compared to the variability going back 600,000 years or more. These are largely accounted for by things like the ice ages and, changes in the tilt of the Earth's atmosphere axis, and so that accounts for some of the changes in at one point the Earth was covered and carpeted in a lot more forests, so there would be less CO2 in the atmosphere. Today, we're all the way up at 427 parts per million. So this, ended right here at 400. We've already gone higher. And so you know all about the IPCC. These are the AR5 reports. No, AR4, AR5. Anyway, these were based, AR5. We're in the middle of AR7 now. AR6 was released in 2020-22. So, yeah, they're a little dated, I admit. But the point here is that there are three working groups. One, which is just a physical science basis of climate change. One, which looks, and this is where most of the geographers have been active, working on concepts such as vulnerability, is the group on impacts, adaptation, and vulnerability. And that's where I know most of the people that work in this area. And then working group 3 is much more on mitigation and adaptation of climate change. It's basically looking at what we need to do from a policy perspective to constrain climate change. The IPCC is very clear that the levels of concentration of 3 major greenhouse gases the biggest of which is carbon dioxide, highest in percentage terms in the atmosphere. But methane is also really important. It's a much smaller percentage term, but its heating capacity in the atmosphere is much higher. And nitrous oxide have increased to levels unprecedented in at least the last 800,000 years. They've increased by 40% since pre-industrial levels, CO2. And then land use. So this, this idea, is this driven by emissions? Yes, it is. It's settled science. We don't need to go back to that. And this is the current levels. And these are the projected levels out to around 2100. What you can see is that this was back, presented as of about maybe 8 to 10 years ago at most. And they were saying at that time that the lower scenario would be somewhere around 450 parts per million. At current trajectories, it doesn't look like we're going to reach that. We're going to blow well past that, and we may well end up in this higher scenario of close to 1,000 parts per million in CO2. Okay, question number 2. Anyone want to answer this? Yes. The answer is yes. This is how we know it, is based on, a network of climatological or weather meteorological stations and a network of buoys in different parts of the Pacific and Atlantic major oceans. And frankly, there's also satellite measurements increasingly and things like that. What you will notice is that these measurements are not equally dispersed across the surface of the Earth. So from a data science perspective, you need to realize that some regions of the world where I study, for instance, West Africa and Central America, just have much weaker networks of meteorological monitoring stations. So what we know about the past, Professor Rahman correctly said, we need to know past patterns of change and variability in order to understand what might happen in the future. Unfortunately, our understanding of the past is also constrained because of our lack of data collection in some parts of the world. So this is the temperature record based on land and ocean data from NASA GIS. You can go to the same website unless it's been dismantled by the current administration, but presumably you can go here and get like today's average annual increase in mean. If someone has an internet and wants to go do that, maybe you can shout out what you get. data.gis.nasa.gov/GIS temp. And maybe the URL is also no longer valid. I don't know. But, you're seeing a major increase since the 1880s, since the pre-industrial period or the dawn of the Industrial Revolution and today in average temperatures. And if you look over into the more recent period and look at it as a monthly basis, from the pre-industrial period, we're seeing not just a 0.8 degree increase, but on a monthly basis, in 2023, we saw winter temperatures at 1.8 degrees above the pre-industrial norm globally. So things are really changing. And this sort of shows back in time to the 1940s and 60s, the monthly, that's why it looks like a spaghetti, kind of plate of spaghetti, because it's showing all the years together. But the more recent years are in orange, and all the orange years are at the upper side of this chart. So what are some of the impacts of a warming world? Most of you are already aware of this. I've been talking to some of you about work that you're doing on glaciers. There's increased temperatures over land, snow cover is decreasing, air temperature is increasing, water vapor is increasing, sea ice is declining, marine air temperatures are increasing, sea surface temperature are increasing, sea level is increasing, ocean heat contact. So all of these are consistent. Every single one of these is consistent with what we would hypothesize would happen in the case of a warming world. This is other observations, just confirming what I just said about temperatures over the oceans, sea surface temperatures, sea levels rising, snow cover declining, glacial mass balance, going down substantially. Each of these is consistent with what we would think of in a changing climate. This is sea surface temperatures, and it's the same kind of plot showing daily, though, not monthly. And you essentially see that in February of 2024, it reached a new high. Sorry, these are temperatures in Fahrenheit, so that's what we still use in the U.S. But it's increasing. And then observed climate change impacts. This was a data set that we disseminate through something that we run at our center called the IPCC Data Distribution Center. And it's a database that shows you where in the world there have been studies of observed climate change impacts largely on ecosystems, hydrology. So you can see, terrestrial biological systems, marine biological, hydrology, cryosphere. And one of the things you'll notice if you saw a global map, excuse me. One of the things you would notice if you saw a global map is that, again, most of these studies are concentrated in the global north, and particularly in Europe and North America. So, this is 2013, but it hasn't changed much since in a decade when they released the AR6 report. The AR6 report said the same thing. Basically, warming of the climate system is unequivocal. We've observed unprecedented changes over decades to millennia. In the atmosphere and ocean have warmed, the amounts of snow and ice have diminished, etc. Here's an example from Arctic sea ice, shows the extent of our Arctic sea ice, and this was as of last September. You can see this is the average summer minimum. So this is the usual minimum amount of sea ice from the period of 1980s to 2010. And as of that September 2024, this is important for a number of reasons, but mainly from a climate perspective, it's important for albedo. The Earth's albedo is shifting, it's growing smaller, the reflectivity of the planet, we'll see in a second, the glacial sheets are also melting. This ice, from a sea level rise perspective, doesn't matter, because when you have ice sitting, an ice cube in water when it melts, it doesn't raise the water in your glass, it stays the same level. In the same way, ice that's floating on the sea doesn't raise the level of the seas. But this stuff, oh boy, that's right there. You're looking at about, I think, I've heard something like 6 to 7 meters sea level rise. Right there, just there. We're not even talking about Antarctica. So that's a lot, right, for our coastal zones. So this is what's happening with Greenland, speaking of which. It's melting in the average melt day area anomaly. Going back to the past, you're seeing much more melting extent, larger areas, and you're seeing areas melted every year increasing. But glaciers are also retreating. We've seen this in the Himalaya, the Andes, the Rockies, and we have these wonderful photos going back till the 19th century, even in some cases, of Swiss glaciers retreating, and what used to be covering a whole valley now is leaving a glacial lake at its mouth. So what's causing the warming? Are we getting closer to the sun? No. Are solar flares? No. No, these are all trick questions. CO2, methane, NO2, etc. So this is the temperature in CO2. So what you see, is scientists have been able to track the level of CO2 in the atmosphere going back, and of temperatures based on a number of proxies that they have. So we don't have weather stations going back 700,000 years, but through paleoclimatology, dendrochronology, a whole range of different proxies, sediments in the ocean floor, they have a pretty good idea of what temperatures were in the past, types of plants, the plant distribution, pollen, things of that sort. So they can tell what the temperatures were. So reconstructing, you can see that basically temperature has been more or less in lockstep with CO2 for a long time, going back 800,000 years. Okay, so this all comes back to this, something that I didn't mention earlier, but the amount of watts per meter square entering the atmosphere, you might notice, balances roughly the amount of watts per meter square leaving the atmosphere. So that's what's kept us in that nice zone. But now what we're doing is we're kind of reducing the amount of outgoing long wave essentially through the increase in CO2. There's more that you could say about the nature of the different molecules, the way these CO2, methane, et cetera, are chemically constructed and the way they vibrate when they warm up. And that accounts for some of the fact that they actually warm the atmosphere more than other molecules of gas. So nitrogen doesn't really change. The nitrogen, which is a major component of the atmosphere, is relatively inert and it doesn't react to temperature in the same way that CO2, H2O, water, and other molecules interact when they're heated, when they're warmed up. So we can talk about what happened in the past, in part by building climate models. So if you build a climate model and you go back to 1900 and you run that model against observations in the dark black lines, you see basically in a world in which there's really no CO2 emissions and the atmosphere remains the same, that essentially the models would show that we actually are going to get, we warmed a bit in the middle of the century, last century, but we would be expected to be even slightly cooler by the end of the century. But when you add CO2 and other greenhouse gases into the equation, well, the models do a pretty good job of showing you what the actual temperatures have been increased. So the models are able to capture that pretty well. So this is the statement on global warming attribution from, again, the AR5. Is it extremely likely, 95% confidence, more than half of the observed increase in global average surface temperature from 1951 to 2010 was caused by anthropogenic increases in greenhouse gas concentration and other anthropogenic forcings together. Other anthropogenic forcings are largely land cover changes, which I won't talk about so much in this presentation, but they're also an important factor. Not as important, but they're important. What does the future hold? So using the same climate models, and I'll talk a little bit more about climate modeling in a bit, but we basically talk about different representative concentration pathways. And these are changes in watts per meter squared at the ground. So 8.5 is 8.5, a change of 8.5 watts per meter square on the surface of the Earth for every square meter of the planet. So, you look at a white light bulb and it may be a 10-watt bulb, and then if you bought a 20-watt bulb and you said, that's a 10-watt difference, say, no big deal, right? That's just a 10-watt difference. It's not going to change in the amount of energy it emits. Maybe the amount of warmth that it produces will not be that dramatic. But in the case of climate, when you warm that much of the planet's surface over the entire surface, it creates huge and dramatic and rippling effects that are going to be the focus of a bit more of our conversation over this week. So the 8.5, some people originally, and I'll be one of those people who in the early days, like a decade ago, we thought of 8.5 as kind of business as usual. You know what the business as usual, that means like if we just keep on our current course. More climate scientists are basically saying that's kind of a possible but low probability outcome. So it's not really the same as what used to be, in the early days they had something called the stress scenarios, the special report on scenarios, on emission scenarios. And the special report on the stress basically had I think it was A1B, or it was one of these scenarios that was considered a high-end scenario. And that was often considered to be like the business. If we don't do anything, no policy, no climate policy, and we keep on emitting, that's what the Earth will look like. That's the heating that we'll get as a result. Now they consider this 8.5 is kind of like low probability according to many. But others like the RCP 6.0 here are definitely like more or less where we're headed right now, and unless we do dramatic efforts to change our policies. So radiative, just an important term here, radiative forcing is the measurement of the capacity of a gas or other forcing agents to affect the energy balance, thereby contributing to climate change. So I just wanted to point that out. So one of the implications of this warming is a shift in extremes. So under the old climate, we had a certain pattern of cold weather and warm weather, which would be this pink area. In a new climate, we're seeing an increase in the area that is now in extreme hot temperatures, but fewer areas, or maybe none, that are under extreme cold scenarios, right? But it doesn't mean that the extreme colds don't exist and they don't occur occasionally. And sometimes people make erroneous claims about the fact that it was really cold last winter and therefore climate change must not be happening. We know that climate is on average over longer periods of time, whereas weather occurs, in shorter cycles, right? So the other thing that, in the way that this may not be entirely correct as a diagram, is that this is actually flattening. Okay, so what does that mean? If you have to contain the same amount of distribution of whatever it is, precipitation or hot or cold temperature, basically means your extremes are getting more extreme in either direction in some ways. So we're seeing a shift. So this is, I was talking earlier about the risk framing under the IPCC, so this is a perfect example. Anyone in the insurance industry will understand what this means. You roll the die. How many times do you expect it to come up? 6. Normally it should be 1 in 6. But if you weight the die, you're going to get, and you weight it so that 6 comes up all the time, or not all the time, but let's say instead of 1 in 6 times, it comes in 1 in 4 times or 1 in 3 times. Then you're suddenly, your risk is going through the roof. And so this is a shifting distribution just, I believe, this is in the world, I guess, for the whole world, not just for the US, but basically it's looking at the shifting distribution of summer temperature anomalies. And it's showing that by even the 2010 period, 2011, that we're seeing many more high temperature anomalies. So that's that shift that I was just talking about. This is just, again, a little bit dated, but looking at the proportion of summers by 2080 to 2100 that will be hotter than the hottest summer on record from the past. So pretty much most of Asia, South Asia, and much of Africa will, in the future, have summer temperatures that are 100% of the time hotter than anything that we've experienced to date. And then this is the number of heat deaths in Manhattan. It's one reason I'm going to be talking to my wife when I get back, because I was reminded when I looked at this, we live in Manhattan. So I'm like, honey, we're getting older, and things are not looking good. It's going to get a lot hotter. But basically, we expect there to be and these are, this is so old, they're using the old A2, B1, the stress scenarios, but basically you have high and low emissions, and under a high emission scenario, the heat effect goes up by 50 to 90% in terms of mortality. Precipitation and drought are going to change, and we'll see a lot of changes. So wherever you see yellow to brown, it's basically fairly dramatic, 20 to 30%, up to 50% changes in declines in precipitation. In some areas, we'll see increases. India, according to this particular scenario, out to 2080 to 2100, is, likely to see, something like a 10 to 20% increase in precip. But there's also evapotranspiration, which is a result of temperature increases. So you can increase the precip, which in many parts of the Sahel zone, for instance, in the eastern Sahel, they're likely to see maybe significant increases in precipitation, but we know temperatures are going to be really a lot hotter there, and so net you may see some declines in actual available water, basically soil moisture. If you want to measure the fundamental variable that's important for agriculture, is soil moisture, and you're going to see declines in soil moisture. So one of the things you'll see, and pretty much all models reproduce this, is an increase in the mid-latitude, well, it's kind of the slightly extratropical zone of drylands. So we're already seeing this to a large degree, a drying in the Mediterranean region, a drying in parts of southwest US, and also in Australia, southern Africa, and just below the equator in Brazil. And in a moment, I should show, right now, I'm going to show you why that is. What's happening is the Hadley cell, which is, this is just looking, imagine this is the Earth curves like this, but they flatten out the curve, and you're looking at it as a straight line. And you're looking at a cross section, let's just say towards the east, of the major wind systems and the pressure systems. And so you have a very low pressure zone over the equator. It's known as the intertropical convergence zone. This is where a lot of the rainfall occurs. That's why you get a monsoon every year in India as the temperatures heat up over the land and the monsoon area moves north. You get that rainfall. Same thing in West Africa. And what's happening, though, is this Hadley cell is expanding and flattening out and going more towards the north. And so that's going to result in increasing drought conditions, because this is a high pressure area. When high pressure prevails, you get drought typically. When low pressure prevails, you get more rainfall. And feel free, if anyone's an atmospheric scientist here and wants to correct anything I said, raise your hand and feel free to do that, because I think I'm getting it mostly correct, but there may be nuances. So other things we're seeing is increases in daily heavy precipitation. I know in India this is a big issue. I mentioned the Mumbai flood in 2005, but when you have a warming atmosphere, it carries more moisture, and that moisture can come down in very rapid cloudbursts of precipitation. Hopefully we don't see too much of that this week, but I saw that rain was forecasted for one of the days. And so basically, every model basically projects many more very wet days, meaning days with extremely high rainfall. And then rainfall intensity is projected to increase in the different areas out to 2080 to the 2100 mark. But in some areas, rainfall intensity is projected to be lower. So I'm not sure why that is. But you see areas of southern India, for instance, where rainfall intensity is expected to get more and more. Sea level rise, we know sea levels are rising based on tide gauge and satellite altimetry information, and this shows some of the projections. I personally, if there's a lot of uncertainty around this, so the West Antarctic ice sheet you might have heard about, if that were to suddenly start moving at a much more rapid clip, I think we could blow through a meter in this century and go higher. So the fact is that the cryosphere science is very good, but they still have a lot of uncertainties, and they don't know how quickly some of these things will unfold. But the best science back, at least until recently, was that sea level rise would be in the kind of under a meter level at a maximum. And that's also extremely regionally variable. So geography is very important. And so you have areas like delta regions where there's subsidence going on. You've got areas of uplift where actually some of the islands, like the Maldives, are actually, they're in areas of uplift. So if anything, they might actually outrun, sea level rise at some, depending on how quickly they rise. But this shows India below 3 meters. So it gives you an idea. I believe some of you, raise your hand if you're working in this region. So I see 3 or 4 hands. Great. So, that's a really important issue. You have both cyclones and you have sea level rise going on there. So what are some of the impacts of all this? This is what's called the burning embers diagram from the IPCC. And what it says is basically what is the risk due to climate change? If it's darker purple, it means based on a certain temperature change, you will see, and the purple zone, that means there's a very high risk. So warm water corals are at very high risk even at a 1.5 degree temperature change. Mangroves, maybe a little bit more robust. Fisheries, kind of in the middle. Arctic region, very highly at risk based on, just at a 2 meter level. Terrestrially, because anyway, you can go down the line here and see which areas and which sectors, like tourism, are at most risk based on different temperature changes. This is just an example of one climate impact in 1 year. So these were sort of this is the average trajectory of corn yields in the U.S. from 1940 onwards, when we started mechanizing heavily, increasing pesticide and chemical fertilizer use, and also some of this might be resulting from CO2, what we call CO2 fertilization effects that actually increases yields to a degree. But in 2012, there was a major drought in the Midwest of the U.S., and that suddenly the yields dropped down by roughly, almost, well, you could say about a decade or 2 decades worth of yield was just cut off in 1 year by a drought. And this describes some of the impacts. The total cost was $30 billion and shows a guy looking at pretty dry ground. Other issues that we're going to see increasingly is the effect of high temperatures on recreation, but particularly outdoor labor. And I think this is a huge issue in India, and all of you are aware of it, is outdoor laborers, construction and agriculture increasingly are going to, face real constraints. Their labor productivity will decline, and health-related issues are going to be on the rise. Kidney disease is one of those things. And unless you drink a lot of water when you're out in those kinds of high temperatures, the impact is really quite dramatic. And sea level rise. So this is just the same kind of map that I showed earlier, but for New York area where I'm from. And then you've got what I find interesting from a climate mobility perspective, and I chaired a conference last month that was called MR 2025, Mobility and Resilience 2025. And at that conference, we were talking about the potential to buy out housing and buy out and do policy measures that might restrict growth in some of these sea level rise prone areas of the coastal zone. Wonderful in principle, but I pointed out that census data just shows that all the growth is occurring in many of these areas that are most highly impacted by sea level rise, and now increasingly forest fires in Los Angeles and places like that. So we're talking about swimming against the tide. The tide is coming in and we're trying to swim and change things, but it's often very hard to change them. This is a database that the Trump administration also discontinued because they didn't really want to hear about it, but it shows the increase over time in the number of billion-dollar disasters. So any disasters over $1 billion are registered in this database. And you can see that it's just increased over time. If you looked at the more recent bars, some of the things like the LA fires and the, you're just talking about increases that are quite dramatic. Tipping points. This is another big issue in climate science and an area of extreme uncertainty, but there could be changes that occur that create positive feedbacks. So the positive feedbacks include things like if you warm the permafrost in the north, things like methane can be released by that permafrost that is melted. You have, essentially huge reservoirs of methane in the polar regions that could be released into the atmosphere, creating a positive feedback. Boreal forests are already increasingly susceptible to forest fires. I mentioned a little bit about the risk of Amazon forest becoming more of a steppe or a dryland area. And one of the other feedbacks that I was learning a lot more about at this conference last week at Scenarios Forum, because I wanted to go to some of the sessions on tipping points, which I find to be an interesting area, is this idea that the AMOC, the Atlantic Meridional Ocean Current, so this is basically a current, a warm water that keeps Europe in nice temperatures, because you have what's called the Gulf Stream. The Gulf Stream is actually winds. It's a pattern of, it's an atmospheric pattern in which that warm water warms the air above it, and then that air is transported and blows all the way up into Europe, northern Europe. You would have uninhabitable conditions in places like Norway and England and other places. Well, not totally uninhabitable, but they would become a lot less hospitable, let's put it that way, because if you turn this current off, if you turn off the AMOC. So the AMOC it turns out ocean currents are critical to understanding how tipping points might occur. And part of the reason those might be disrupted is because you're melting so much really cold water, the ice water that's coming off the glaciers in the ice sheets of Greenland, and they're going to upset this gyre that occurs in the northern Atlantic, and in complex ways may cut off this transport of heat to, and I saw maps showing what might happen with corn yields and wheat yields in the future. And it's quite dramatic. We're talking about large areas, the corn belt of the U.S. and wheat growing areas of Russia and Ukraine that suddenly you can't produce those crops anymore. And it would be, in a way, startling because we're expecting warming everywhere, but this would actually cause a dramatic shift in colder temperatures in those areas. All right, so we've seen that some bad things could happen. What we do depends on solutions, and here we just look at efforts to curtail some of these greenhouse gases. Everything on this side of the line results in warming, and everything on this side of the line results in cooling. And what we want to do is decrease the red lines, the red bars, and increase the blue bars, right? Absorb more carbon in land activities, and transition to things like solar. And so these are some of the wedges, they call them, in terms of changing emissions. So reducing by being more efficient, reducing increasing vehicle passenger efficiency, heavy trucks, expanding renewable energy use, capturing and storing, etc. And each of these wedges can reduce, at least in the U.S., we're talking about reduce the amount of emissions. So we need to move towards a more sustainable mix of energies. I was just in the UK and was struck that probably, it looked to me like maybe 10% of the vehicle fleet now is electric EVs, which in the US, we're very far from that. China, I think it's closer to like 50%. I don't know what it is in India, but there's huge potential to increase EV usage. And all the seeming fear that people have about moving to EV, I think is maybe unwarranted as long as we do it using renewable energies. And then population, I didn't put this in, by the way, but my colleagues in the climate science side, they put the people in, because yes, population is a factor. This is something, it was really a thought experiment I did back in about 15 years ago. And I was just kind of curious. So Americans don't really know what a ton of CO2 looks like. Do you know what a ton of CO2 looks like? Can you imagine a ton of CO2? I can't. I have a hard time imagining what a ton of CO2, what a gas, a ton of a gas looks like. Well, it could be. You could use your imagination. My imagination led me to say, what is a ton of CO2 in gallons of gasoline? Because Americans understand what a gallon is because every time they go to buy some milk, they buy it in a gallon jug, okay? All right? So we can actually imagine what a gallon of gasoline looks like. Every time we fill up our tank, we know it's roughly 10 to 15 gallons. If it's an SUV, it might be 20 to 30 gallons. So I did the thought experiment to say, if every country in the world equitably consumed the same amount of CO2 in terms of gallons of gasoline, what would we need to do to get to a point where everyone is equitably consuming a sustainable level, not just consuming at the same level, but a level that would bring us some level of climate stabilization? The US would have to go from roughly 2,500 gallons of gasoline per person down to 100 gallons of gasoline. India, you guys don't have such a great challenge, or didn't when I did this calculation. And so you're around 250, and you have to just have the number to about 100 gallons per gasoline. But one point I make with my American colleagues is that 100 gallons of gasoline is basically going with your Ford Explorer, which is one of the biggest SUVs that they drive in the US, and you fill it up 3 times and you're done. That's it. You've used your allocation for the year, and but how does the economy run? How does the government run? How does anything else run? There's nothing left over. So our challenge is really quite huge, and it's getting, we made some baby steps, but we're not nearly there. Then you have the problem of attitudes and beliefs, and of course, this is where I asked you your question, are we getting closer to the sun? Is the sun increasing its output? These are the kinds of responses that you get. And in the US, at the time they did this poll, roughly 31% people said it's the ozone hole that's causing the climate change. Another 7% said that we've got increased output. The heat from the sun is getting more. And then, of course, the Earth's orbit is getting closer to the sun. So all this nonsense stuff, and that's all social media and crap science that's being perpetuated. India, not a lot better. Sorry, guys, but there's some room for improvement. All right, where am I? How much time? I have about 10 minutes. So I'll cover some other areas, and if I don't get through the whole thing, no problem. Nobody's fallen asleep yet, which is pretty amazing. I did see you nodding off, Professor Raman, but you're forgiven because you've been working so hard to put this together. I do the same thing, frankly. If you have to nod off, I will not call you out like I did my good friend. So uncertainty of projections. This is a quote. So doubt is not a pleasant condition, but certainty is an absurd one. So frankly, we'll never get to a point where we know everything we need to know about everything, and we can just, have a state of total knowledge. So why is it important to know about uncertainty? Well, there's an element that's just random, that's a rolling of the dice component. We don't know what's going to come out when we roll the dice. So there's natural variability in the climate system. And frankly, that's just a part of life. It's going to be there's a random element. Total uncertainty, however, is a combination of both the random element and the epistemic uncertainty that we have. That's basically that we just don't know everything there is to know about the world. You remember Donald Rumsfeld? He was the Secretary of Defense. He said, there's the known unknowns, the unknown unknowns, and some other knowns. And basically, we live in this state where we know about some things, but we don't know how it's going to impact things fully, like AI we were talking about earlier. So what's that going to do for energy use? We can hypothesize, we have some conjecture, but we don't know how it's going to affect fossil fuel use, for instance. All that stuff may be powered miraculously by solar, we don't know. But there's just certain things also about interlinkages in the system. We've been talking about complex systems. The system itself is just inherently complex, and we don't fully understand the complexities of this world. So this is how climate models work, and basically, just to simplify it down to the bare bones, you've got emissions, you've got natural perturbations such as solar and volcanic activity, which result in the volcanic activity results in more sulfur dioxide and more high atmospheric particulates. Land use and land cover, that's another area of uncertainty. Then you have observations of these things, and there's uncertainty in the observations, so the data we have are not altogether always correct. They're not always unbiased. There's also measurement errors, things of that sort. Impact models also result in a certain amount of uncertainty, which can then, if you have an impact model that says you're going to see a change in the Amazon, well, that'll affect land use and land cover, but there's uncertainty in that. And then policy and resource management decision making, all of this realm of like what's going to happen, are we going to meet the Paris targets, are all the nationally determined contributions going to be met or not, are they sufficiently high enough to meet the need to reduce greenhouse gases? All of this represents areas of uncertainty. So what about, what do we know? The future trajectory of emissions of greenhouse gases based on these SSPs I was talking about earlier, how the world will develop economically, socially, politically, technology. So that's one area of uncertainty. We can explore that through these various future scenarios, the SSPs being the primary mechanism we use. How the climate system responds to increasing greenhouse gases, explored through the use of climate models. The spatial scales at which climate models are run is an additional source of uncertainty. I'll talk about that in a second. And then natural internal variability in the climate system. There's just a certain amount of natural variability, which is a source of uncertainty. We've talked about these already. Numbers are the amount by which radiative balance would be disturbed if a given pathway were followed. Some are optimistic, some are pessimistic. There are issues around our understanding of the response to forcings. The forcings being, again, the greenhouse gas emissions primarily, but also land cover change. Due to complexity of the climate system and various limitations of the modeling system, different choices about the model, subsystems as well. So these are all choices you make in the modeling process. Different climate models respond differently to external forcings. So that's why not every single model always will produce the same average warming across the globe, and there'll be regional differences as well. The MIPS, the CMIPS, the Climate Model Intercomparison Program, has really helped us to quantify uncertainty. There used to be about 40 different models in CMIP 5. Now there's over 100 models run by 49 different modeling groups. So there's a lot of modeling going out there, and each model has its own particularities about how it represents the Earth system, namely all this stuff that we talked about earlier. You need to have all of these elements accurately mapped in your model in order to basically understand what's going to happen. So how do we simulate this? We create this stacked grid cell system, and we model the physical processes. And each grid cell then is connected to the neighboring grid cells. I'm not a modeler. I don't know all the intricacies. There's a heck of a lot of math that goes into this. Is there a climate modeler in the room? Okay, just curious. Huh? Okay, well, you can raise your hand if you're a climate modeler. And so it's complicated, right? And these guys are very smart, and women. They're all very smart, but you can understand it's not an easy process to get this right. And all these things are important: the amount of sea ice, the amount of water. What we've seen is since 1979. The average sensitivity to a doubling of CO2 in the atmosphere has remained at roughly 3 degrees Celsius. So since the earliest days of climate modeling, we have not been able to change that number. Maybe that's just a robust number, and maybe that's just what it's going to be. But what we have been able to do is shrink the uncertainty around that. So we're no longer facing the same levels of uncertainty as we faced in the past. Does that make sense? So double the amount of CO2, you should see around a 3 degrees warming. So what was the CO2 level again from the charts that we saw earlier, beginning in 1950? 316. So we'd have to get to 630, I guess, parts per million in order to see a 3-degree temperature change. And then, the biggest uncertainty actually, apparently, this is according to my climate science colleagues, has to do whether it's high clouds that you have primarily or low clouds. So more low clouds, more cumulus, those nice fluffy clouds, the nice clouds, they push more radiation out of the atmosphere, more they reflect back. And so this is all about how solar radiation affects and is affected by cloud cover. And part of the issue is also the effect that these clouds have on long-wave outgoing radiation and the way they trap it or let it go through. So it's important to know these things. Just to say that one of the things that I've noticed and I kind of wondered about is, here we are in 2025, right here. So if we were in 1925 and people said, I don't really care what happens beyond 2000, those people, it's a totally different generation, blah, blah, blah. Here we are, we kind of look as if currently we talk about 2100 being a long way off. Well, a child being born today, right, stands, in all probability, they will live to see 2100. So we should stop, I think, thinking about the future as if it ends at 2100, but really start thinking about longer term trajectories. But what's interesting is the number of models that go out beyond 2100 reduces substantially. So you see the number of models that are modeling using these different RCPs declines once you go beyond 2100. I talked a little bit about uncertainty from the climate modeling perspective. So 400 kilometers squared looks, the Rocky Mountains of the US look like that. As you get higher and higher resolution, down to 10 kilometers, you can actually see the real elevation deviations. So averaging over large areas tends to produce uncertainty. I think I'll skip this. This just shows effects of different climate resolutions on the precipitation in the current period. So it kind of gives you an idea of how resolution affects the representation of one physical parameter. There's also natural variability. There's been a lot of change. There's change year on year. I'm not going to go into this as much. There's also uncertainty around when we're going to reach net zero emissions. And, the idea was that somehow we should try to really move quickly and smoothly to a net zero transition by 2050. But we keep pushing that date out. So the longer you push it out, the more dramatic the transition has to be and the more quickly you have to move to net zero. How does this all relate? This is kind of interesting, and it'll be a thought experiment really for you to think about, because I didn't really believe this work, and I heard about it before, but then a colleague explained it to me. I said, maybe there's a point to this. So how does all this climate science relate to climate mobility? So you heard earlier about the Hadley cells I was talking about, in the way that the circulation of the atmosphere brings high pressure to these belts, and you have much higher, greater degrees of aridity and semi-aridity. So and you see the Hadley cell for most of where it descends, it descends over areas of the ocean for the most part in the southern hemisphere. So there's much more land area in the northern hemisphere where it descends. What you're going to see as a result of increasing heat in the atmosphere and climate change is an expansion or flattening of the Hadley cell. So areas that were to the north of the Hadley cell, like northern France or central France, or maybe parts of Northern California or into Oregon in the U.S. I'm sorry to use these examples. I don't have an equivalent for, and I think my alarm is going off. So this is really the last point I'm going to make, is those areas will now be much drier, and we'll see an expansion of drylands into those areas. Water scarcity may grow more, but these guys came up with a way of talking about having, so this is a new concept that's sort of been floating. I think about this a lot. If you want to talk about it, I might even bring it up in one of my later lectures. But this idea that there's a human climate niche, that places that are more suitable for human habitability than others, with better average annual temperatures and things. Frankly, I was just in the UK and I thought it was, that's a pretty nice climate niche. It was hot last week, but it wasn't that hot, and it cooled off at night quite a bit. But this human climate niche will see declines in suitability as temperatures rise. And so this is sort of a controversial concept. It kind of likens us to animals. And because what do ecologists think about? They think about the niche for different species. And so you could say that it's too simplistic and doesn't have any validity for humans, who are very complex and ability to adapt to different environments. But there's also projections that look at future economic impacts, changes in GDP, and these may seem quite extreme, but these are noted scientists who are actually doing this work, and they look at the real potential impacts on GDP, comparing, looking out to 2100 in a high emission scenario, and so one of the things that you'll see is that. By latitude, temperatures vary less around the tropics. So this is the mid-tropics right here, 20 plus 20 north in the tropical zone. So temperatures don't vary as much. They tend to be high. I'm sorry, again, this is in Fahrenheit. But they start declining rapidly as you move forward from there. And so if you wanted to think about this in terms of a temperature conserving distance, then the way you could think about this is the distance that you would have to travel to get out to maintain the same temperature in 2070 compared to today. And the distance you have to travel northward from India is a lot farther than I would have to travel from New York to get. Like, I might only have to travel 100 kilometers north or 200 kilometers to preserve the same temperature in 2070. I would experience essentially the same climate, more or less, by moving 200 kilometers, whereas you might need to move more like 1,000 kilometers or more north. Now, of course, this varies by altitude, so landforms affect this as well. In the south, the southern hemisphere, as I mentioned, the distance you would have to travel is roughly the same, but you end up with a lot more ocean. So you can't actually move into those areas because they're essentially covered by oceans. Does that make sense? If this is too confusing, disregard it. It's just a thought experiment, really. It's not to say that's what's going to happen, but it's just to say, as a climate scientist, you could look at it from that perspective. And this was an example of work done by one of my colleagues, Adam Sobel and Solomon Sang, and they basically looked at percent of the world population living that would have to migrate various distances to preserve the same temperature in 2070 as they experience today. And, a fairly sizable, roughly a third of the population would only have to move about 500 kilometers. But there's even more, many more people who have to move far longer distances. So with that, I will close and take any questions you may have. I saw it. I'll just take the hands I saw first. So I saw.
Sir, you talked about two models, shared economic pathways and representative concentration pathways. Can we integrate these two, and what would be the data sets or techniques for that?
Thank you so much, sir, for this articulate presentation and taking us to the world of atmospheric and planetary sciences. So the drowsiness didn't hit, or the post-lunch drowsiness wasn't there clearly because of such an interesting demonstration. So my question is more towards the international geopolitics part of how the takeaway from this presentation. So I would like to take your perspective as an American, from somebody coming from a developed world. So, in the COP conferences proceedings, there is the key note of contention is that the global economies, emerging economies like particularly China and India, they are held responsible for the global carbon emissions by and large. But when had a visit to Europe, I found that there are many luxury brands, be it for handbags or any item, of, particularly materialistic brands. Sir, all of them have their industries in countries like Bangladesh, major textile industries. So, when it comes to climate finance, why is there a tug of war between developed and developing world nations? Like, who is responsible for global emissions? Do we need to address the carbon footprint first of an average, say, for example, American, please don't mind that, versus an average Indian? Or is it that we have to see things in the global perspective? If the developing nations, which is true, they are global emitters of carbon right now, currently, but in the developing world, there is no austerity in consumption behavior. For example, in the capitalist market, there's marketing and there's no sustainable fashion there. So, for example, recent controversy of Prada brand where they were producing footwear which were sustainable. So that culminates from the source. The source is India. So we have been a land of sustainable. So when it comes to climate finance, do you address that? If it's a paradox. Thank you.
Those two right now, and then, so in fact, the first question is basically why the SSPs were developed, and you might have noticed if you paid attention was they moved from talking about combinations of SSPs and RCPs, which was SSP 5 and RCP 8.5, et cetera. They started talking about 5-85 to 26 and things like that. And frankly, I was talking to my colleagues. So I sit on a steering committee called Iconics. It's a group that manages the SSP process. And I asked them, because I wasn't actually aware why that happened in the last assessment. They said it was, frankly, nobody consulted with them and it was a mistake. So they started hardwiring into these climate models the idea that SSP 5 is linked to this 8.5 and the SSP 3 is linked to maybe 4.5 or something. And that was not intended to be the case. You're actually supposed to be able to pair the SSPs separately. So you could come up with scenarios in which an SSP4 world generates emissions at the level of, say, 6.0 or whatever. So I'm just, I think that they are definitely meant to be important for use by the climate modelers, but they weren't meant to be hardwired in, because the scenarios themselves are supposed to be a flexible framework for understanding. I was at a workshop in Vienna in June, and basically they were talking about health-related outcomes. But there are people who look at a whole range of different economic. I looked at the last conference, there was someone doing debt to GDP ratios under different SSPs. Fascinating work. And I'll talk more about why I think that's fascinating in a future lecture. But thinking about debt and what the likely debt ratios are in countries as a result of climate mitigation activities and adaptation activities and spending on other social services is really a critical issue, because that's what's going to be what allows us to kind of get to, if government finance runs out or we have governments defaulting, it's going to create a very uncertain world. Yeah, I mean, the whole issue of imports to northern countries, I think, is not well understood by average people, but certainly scientists are understanding the fact that you have to look at essentially the carbon footprint of individuals and where they're sourcing their materials from. And Mattis Vakernagel actually guest lectures in a course that I teach on composite indicators. He's the founder or the folder of the ecological footprint. You might have heard of the ecological footprint. It measures everything in terms of hectares of biologically productive land. He's from Switzerland. I said, how did you come up with this idea? He said, I grew up in the post-war Switzerland where we had to grow all of our food on our land in Switzerland, which you can imagine is a mountainous country with very little arable land. So he became acutely aware of the constraints. So he moved to the U.S. Of course, we believe there's no constraints in the U.S., but he still saw the vital nature, the vital importance of measuring total consumption in a way that people could kind of understand. But I think it does miss some elements like the luxury goods. That's a whole other area. They tend to be, yes, manufactured in countries with maybe lower environmental standards, and the results, the emissions are credited to those countries rather than to the ultimate consumer. So there's been a lot of ways of doing accounting, for this transfer of material, of emissions and transfer of water, the embodied water of various products from imports and exports. It's really critical to know about that. It's certainly very important. I guess maybe we can take one or two more questions and then, sorry, what was it? Okay.
Thank you, Dr. Alex, for your nice presentation. Actually, I have a concern. Okay, we have talked about climate change, global warming, and carbon emission. Okay, my concern is how can climate justice be ensured for those least responsible but most affected by global warming? Okay, this is the concern I have, and I want you to put some insight.
So that's, I'll come back to you. I think you had your hand up, right, earlier? Or did two of you have it? Okay. Well, we'll take three more questions, okay? Let's just do it right now. Quick.
I just have like some add-ons, like on, for example, individual carbon footprint. If it, like, there could be some mechanism possibly that we can develop to address that. But what's the larger context in the geopolitical connotation where we see the conventional war being started? And I reminded of the work by Neta C. Crawford, who actually works on charting the US military emission onwards the Second World War, which is like almost equal to the half of the South Asian nation. So particularly in a context that we can work on limiting the individual carbon footprint by the regulation. But who is going to regulate this state?
Sir, there are a lot of models at global, national, subnational level. I was asking about the climate models on the city scale because each cities have urban heat islands and they pose a different climatic scenario than the surrounding areas.
Sir, actually, Sir, actually, I don't have any question, but I want your valuable suggestion on my doubt that we see from the slides that for future modeling, prediction modeling, we need to get well aware of the past data trends, but it is very difficult to get data for the variables like CO2, SO2, for other pollutants on a very small level data, like he is telling, like Varanasi and its suburban areas, and while working for a micro level, for example, like Varanasi and its suburban area, which are now drastically expanding in terms of urbanization. So here is, I want your suggestion. How will it affect the accuracy of that future prediction modeling scenario? First, and then second, what are the ways you can suggest to tackle this real world problem?
So the first, I think, was about climate justice. Most of the emissions coming from the U.S. and North America. All right, you're putting me on the spot now. We'll talk about climate justice. I always kick the ball down the field, right? So we'll talk about climate justice a bit more tomorrow, but or the days will start blending together in my head. But we will talk about it, and clearly it's a huge issue. that, unfortunately, we live in a world with power structures that tend to be heavily influenced by fossil fuel industries and by this notion that countries can only really prosper by burning fossil fuels. And then there's this whole freedom element, and that's one of the backlashes in the U.S. is people don't want to be told what to do. They want to be able to retain their ability to consume. I'm going to ask for 2 words from you because I remember your question, but
Work on charting US climate emission post World War II that is equal to the emission of half of the South.
yeah, no, I mean it's basically the same issue. I mean it's the fact that the U.S. has been profligate in its use of fossil fuels, and in fact, you could say that post World War II we set up the global order so that we could extract the maximum amount of petroleum resources, fossil fuels from the rest of the world, and maintain a certain order that benefited us. No, I know it's a huge issue. Yeah, well, I'm not a huge, I'm not a modeler, I told you, but there are, increasing efforts to localize projections even down to city scales using nested models. And, some of it can be done fairly simply through what they call statistical downscaling, which basically takes the way the patterns that the coarse models generate against data from the historical period and looks at the delta, like the difference, and then they just downscale basing on that same delta from the observed data to the coarse resolution data, and they can then sort of project out what might happen for temperature. Less so for precip. I think precip is much more of a wild card in a lot of the modeling work. There's less certainty in precipitation modeling. And then you had about Varanasi and use emissions data. Emissions data I'm a little less familiar with, but there's clever people who have figured out how to come up with, understand at a country level how much a country is emitting. I think it's basically, huge economic models of trade and measurement of amounts of fossil fuels being burned. And so it really, frankly, from a climate perspective, doesn't matter how much Varanasi burns. Varanasi could disappear off the map and India would still probably burn about the same. I'm not saying it should. I'm just saying, just to be clear, at that micro scale, it doesn't really matter how much is being emitted because it all goes up into the atmosphere. What is the atmosphere? A huge sink. That's what it's viewed at, or what we have historically viewed it as is a sink for all of our pollutants. We just don't think of it that way, right? We know where our trash goes. It goes to a big landfill or gets burned in an incinerator. But the atmosphere is a sink for all the things that we burn. One more.
Probably नहीं, कल.
Thank you, sir, for the informative lecture. And my question is on climate model downscaling. When we downscale at the regional level or local level, we didn't even consider the socio-economic or political nuance at the local level. So how this is reliable enough for the local level climate modeling?
Just to be sure I understand what you're asking, how do you downscale the socioeconomic scenarios?
When we use statistical modeling like quantile mapping or any other statistical downscaling method, we didn't even consider the socioeconomic pathways. So the name is socioeconomic pathways, but we didn't even consider the data. So how this?
Yeah. Well, the global climate models, so you're downscaling from some coarser resolution model, and all of those models should at some level understand what the SSPs are. So it's not as important when you're downscaling, whatever method you use to downscale, it's not as important for you to understand what this SSP will be for that local area for the same reason that it doesn't matter how much greenhouse gases Varanasi emits or what the local economy of Varanasi is. It doesn't really matter for the atmosphere because it's these global level emissions that are more important. I don't know if I answered your question, but I'll be delighted to talk offline with any of you. So.
Thank you so much. That shows the beauty of Dr. Alex, that he has generated energy to the participant. and that is his scholarship, that he wake you up in the post-lunch session. That is the most difficult task, I know, as a teacher. Uh, I was a little bit, tired in the sense that I have eaten more than you. Anyways, so friends, we have a very good session, one very good inaugural session, and one session on very nice presentation on population and climate change. He very nicely related with a lot of data, how the population is related with the climate change issues. And the second post-lunch session was second lecture was on what he showed, the climate change and social vulnerability of different parts of the world, as mentioned before that. And the third session was on climate science and climate change. That was one of the most important. All lectures were so very important, and with fact and precise research that has been conducted by various scientists. And Alex Sebastian's group at Columbia Climate Change Center and other places. So, friends, that is all today. Yeah.
There's more. So bear with me. I'd like to do the little exercise to get to know you better. I'm just going to ask you a few things outside this room, and we're going to go and you're going to vote with your feet. That means you basically move to the group that's represented. First, I'm just going to say, if you're female, move over here. If you're male, move over there. That'll just be the illustration at first. Then I'll ask you a few more questions, and I just want to get to know you better, where you're coming from, what some of the disciplines are represented in the room, etc. So that's the vote with your feet exercise. Hopefully you understood. When you're asked to move into a group, I'll point out the areas you should move to, and you move to the group that you identify with most. You don't have to be 100%, like I know some of you are interdisciplinary. So if I say, are you a physical scientist or a social scientist, move to the one you think you lean towards more. I would say I'm more of a social scientist, but The other thing is, tonight I'm going to send around very shortly a link to the exercise we're going to do tomorrow afternoon. Okay, so this is the tutorial. You will need to read one article, and I'm going to ask you to sign up in a sheet. There's what we talk about, climate mobility archetypes. Okay, different types of situations geographically. I mentioned coastal areas, mountain areas, dryland areas, urban areas. And what you'll be asked to do is choose one of those areas and then choose one of the readings. When you sign up, pay attention to what readings other people are choosing, because there's only 2 readings per group. If everyone reads only one of the articles, you'll have no perspective to bring from the other side. So that's why I want you to choose a group. And if you see everyone's heaping on to highland areas, regions of mountains, try to self-distribute yourself. If you sign up earlier, you'll have a better chance. So I'll send out the email in a little bit, and then there'll be a link, and you'll be able to sign up in a sign-up sheet. So the descriptor is what you'll get. It's a document. It's a Google Doc. The description of the exercise is there. And then the link at the very top of the Google Doc will point you to a sign-up sheet. So you'll sign up in that sign-up sheet. And you can scan the document first and see what the 5 or 10, there's like 10 different archetypes that I'm talking about. And then you'll choose one of the readings. Does that make sense? Everybody's nodding. They're saying yes. Remember, if you see all your neighbors signing up for one of the readings, do the other one. And they're all equally good. They're great readings. And then what I'll do is, on the same Google Drive that Professor Rahman has set up for you, I'll put all the readings in that drive. So it's going to take me about an hour to get all this set up, and then we'll send out an email. So if you see me rushing from here after the exercise, don't grab me by the shirt and say, I want to talk to you about my PhD dissertation, but let me go to the room and take care of that so that you'll have an exercise. Then you can grab me by the shirt later over dinner. I'll be happy to anytime chat about your PhD. And I don't want to say that in a dismissive way. I really am very interested in the work that each of you is doing. So did you have anything more you wanted to say, Professor?
So we call it a day. We go outside and we make a group, as rightly said by Dr. Alex. And tomorrow morning we'll meet with a fresh mind, with fresh energy. Thank you so much. 10 o'clock.